Hello? Hello? You're just in time. I didn't do the problems yet.
Wait, what?
I didn't really do the problems.
Oh, okay. Wait, do you have the solution?
No, I'll figure them out.
Do you have the answer?
No. Do you have the answers?
Wait, no. Wait, they didn't send them to you?
Oh, no.
Wait, oh no. I told them to send them to you.
Am I supposed to have the answers?
Yeah.
Where are the
I
answers?
know the answers to like the first. Okay, so now I give you 6 problems.
Oh, no.
And I know the answers to the first 4 from talking to other people.
Okay.
I don't know the answers to the others.
In that case, I need to get the answers. I don't know the
Yeah.
answers. So,
Because they said that we aren't allowed to talk about the problems until the live stream, so no one's allowed to talk about it.
oh, no.
So I didn't have any way to get the answers.
Okay, well, we're going to have some fun. Oh, yes, I see. I think they said that we forgot to mute the line.
Wait, what?
It's okay. Yeah, let's see if we can figure out all these problems now. And all of you listening on the live stream, we're going to be here soon. Hello, I'm actually going to turn the microphone on the right way this time. Good to see everybody and welcome back to Ask Math Anything, except that we're doing an interesting collaboration today. Today we're going to collaborate with the Lexington Math Tournament. And some of you may have heard as you were maybe, if you showed up early for this live stream, you may have heard that, well, I actually haven't done any of these problems yet. So let's go and try to figure out how to do some of these. Actually, I also just realized that what we need to do is we need to make sure we pull the exact questions down from the slides. Just a second. So actually, what I normally do, if you've been here before, you've noticed that usually what we do is we just talk about any kind of question anyone might ask. And indeed, that's what this normally is about. That's why it's called Ask Math Anything. But actually, what we do today, and whenever we're going to collaborate with anyone who's doing a math competition, is we talk a little bit about some of the questions that they were working on. So there was a fun competition that was going on this week. Apparently for 6 days, people were working on math problems made by Lexington High School. And let me just download these right now. People were working on these math problems from Lexington High School for the past 6 days. Now, these are tough questions. They were designed for middle school students, and they were designed with a lot of time. The area that Lexington High School is in is one of these which has some of the most math competition superstars in the country. So these are supposed to be hard. I guess that means I'm going to be up for a challenge today as I attempt to do some of these. One moment, please, as I move this all over here. All right. And it says no signal because I'm just moving the file into here. Perfect, we got it. Okay. Check. And now we have signal. So the first question, let's start playing with these problems. And I've put these here, I thought about it. I was thinking, should I go and try to do them all in advance, or should I maybe just do them on the spot? I decided to do them on the spot because we know that there are people who watch this live stream who didn't play inside this Lexington Math Tournament. And what we're going to do is we only have 1 hour. And so what I wanted to do with this is do some of the fun early questions and also talk a little bit about one or two of these harder end questions. So, of course, we're not going to have time to go over all 30 of them, but this will help to give a highlight. This will help to acknowledge the hard work that the organizers of the Lexington Math Tournament did, and we can have some fun. So what do we see here? Question number 1. Compute the smallest non-negative integer that can be written as the sum of 2020 distinct integers. Well, what would you do? Does anyone have any ideas? If you're going to try to make a number of distinct integers, well, maybe the best you could do is something like 0 plus 1 plus 2. Oh no, we can do better than this. A lot of people are seeming to say that the answer is 0. Is that right? Let's try. You see, 2020 is an even number. If I was able to have an odd number of them, I could do something interesting. I see people are saying negatives, right? Because if I needed to have something that's the sum of 3 distinct integers, that's not so bad. Minus 1 plus 0 plus 1. What this is indicating is we really want to see if we could get 0. So what can we do? Well, if I want to get 2020 of these distinct integers, I could run them maybe in some kind of a sequence. What if I try to put them all next to each other? Like 1010 is about half of 2020. So what if I made my numbers 1, 2, up until 1010? Okay, that's 1010 numbers. And then also, let's go the other way. 0, negative 1, all the way to minus 1009. Okay, so if I did this particular set of numbers, I'm not telling you this is definitely the right answer yet. If I make this the entire set of numbers, well, that wouldn't be so good because if I made this, I'd get a sum of 1010. But I'm already seeing some people say it doesn't have to be consecutive. It's a trick question. This is question number 1 after all. What if you did this? Oh my, if you did this, then you happen to have all of the negatives cancel all the positives. And the answer actually happens to be 0. And 0 is a non-negative integer. So the answer appears to be 0. Is that right? I have an assistant here today, and the assistant says this is right. So we've gotten this question right. The answer to a question is sometimes nothing. What's next? Ooh, I have a tetrahedron, ABCD. It's as shown below. And we want to find the number of ways to start at A and walk along some path of edges, and you need to come back to A, but you can't walk over the same edge twice. How could you do this? Well, if you look at this, you want to start from A and walk around and come back. And you can't walk over the same edge twice, so let's start playing around, see what happens. If I start from A, if I just happen to go to B, that's a choice, right? I'm trying to see what kind of shapes I could get. I could, for example, get a triangle. I could do this. That's one kind of shape. Is there any length that's longer than 3 steps? You can see how I'm trying to piece this problem together. It's like, well, if I use a 3-segment path, there's a bunch of these. How many of these? Let's do that first. How many 3-segment paths can I get? I can have, it's basically you go along the face of a triangle, and there's like, for each face of the triangle, you can go around one way, or you can go around the other way, right? So it looks to me that if I'm looking at the 3 edge paths, we're not saying that's all of them, but for the 3 edge paths, I have 3 triangles that are touching A. This is the number of triangles. Triangles on A. Times each triangle I have 2 ways, so I have 6 so far. But that's not the only kind of thing I could do. I can also go and take longer walks. Let's try. Suppose I start from A, because you should always start from A. If you go to A to B, oh, I see, I can go to C and D and get back. That seems reasonable. I can actually go, oh, this is neat. It's a tetrahedron. Any order of the 4 that I want, I could use. I mean, I start from A and I go in any order of the other 3, because every edge is there. Some people are asking, how hard is this? This is a math contest that is much harder than math counts. You have like 6 days to do these problems that we're trying to do instantly, okay? So fortunately, there are people watching the live stream who already did them, and they can even help give hints. So now when we have this, I see that for the paths of length 4, if I'm going to take 4 edges, then the number of ways to start from A and then come back to A is that there are 3 other vertices that I need to go to in some order. So there are, of the 4 edges paths, there are 3 factorial orderings of B, C, D, which is 6. So that's how many 4-edge paths there are. How many 5-edge paths are there? Do I have an extra slide? Yes, I do. Could I make 5 steps and get back to A? Well, there are 6 things altogether. So if there are 6 things altogether, how would you do it? You actually can't. I mean, somehow, first of all, you can't do it. There are no 6-edge paths. A 6-edge path would use everything exactly once. And the reason you can't do that is because the degree, the number of edges coming out of A, is an odd number. So you can't do that. And if you wanted to try to make a walk that went around and used all but one of the edges, there's an easy way to see why that's impossible. Let's pretend I tried to say, hey, I've got this magic walk. It goes around all of the edges exactly once, except for that one in the back. Okay, it just doesn't use that one in the back. And why this is not possible is because there's some vertex here, not vertex. There's some vertex here which has an odd number of edges coming out of it. And if you ever take a complete loop and come back to where you start, you actually go in and out of every vertex exactly an even number of times, like in and out, in and out, in and out. And so if I said I've got a 5-edge thing that doesn't go through here, that's false, because this thing has a degree, a number of things coming out, which is odd. That's the easy way to see that you can't do this. So there's no 5-edge, no 6-edge, and my answer is 6 plus 6, and that matches what people have said so far in the chat. I like the answer 12 also, and it looks like we're good. The questions are going to get harder. What happens next? What did they give me next? Ooh, they jumped all the way to question 7. So what we're doing here is we're kind of doing a sampler of a bunch of questions, and some of the ones at the end are crazy hard. So we're kind of walking through all of these. I apologize. I'm not giving you a complete walkthrough of the entire contest. It's very difficult in 1 hour to talk about the questions that you've been thinking about for like 6 days. But we'll do some interesting ones. Okay, we've got this hexagonal pattern, and it has 2 smaller hexagons per side. That looks like 2 smaller hexagons per side, and it has a total of 30 edges. Maybe I can believe that. We'll see soon. A similar figure is constructed with 20 smaller hexagons per side. how many edges are in the larger figure. Well, we need to figure out how to count edges, right? So the way you would count edges is you just say, hexagons have 6 edges. So you see, look at how many hexagons are in this picture. This picture has 7 hexagons, right? Like 1, 2, 3, 4, 5, 6. It has 7 hexagons. So if I look at this, I have 7 hexagons. And that should be 7 times 6 edges. Right? No, not right. Because it says there are only, what? It says there are only 30 edges. Ah, temp ID is right. There are duplicated edges. Interesting. So I see that there should be 42 edges. But not quite, because a lot of those edges are counted twice. Effectively, what I'm going to do is I'm going to look at this example, figure it out, and then go to the whole scale of the 20. All right? So if I have 7 hexagons and 7 times 6 edges, what's also relevant is how many edges are only counted once. What do I mean? So you see, this particular edge is counted once by the yellow and once by the blue. So it's counted twice. This edge is counted twice. So instead what I need to do is I need to say all the ones in the middle are counted twice. The ones on the outside, those are kind of just like free to go. How many edges are on the outside? Can anyone tell me? On this picture right here? On this picture, if I want to count edges on the outside, how might I do that? Well, I'll look for some kind of a pattern, right? It's like 1, 2, 3. Oh, there's 3 over here. There's 3 over there. When I said 1, 2, 3, what do I mean? I mean 1, 2, 3. That looks like 3. Yeah, so I got 3 things sticking out, and I've got 6 of these all around. So it looks like there are 18 of these which are once only. So of these 7 times 6 edges, it's not quite right. The 7 times 6 edges break into 2 parts. There are 3 times 6, which is 18 of them, which are like counted once. These are like once. But I also need to get out of the way. So I also need to say, of this 7 times 6 edges, all the rest of them got double counted. So the way you should think of this is that 7 times 6 was 42. The remainder is 42 minus 18, which is 12 minus 8 is 4. Okay, cancel that away. 3 minus 1 is 2. Do I believe that 18 plus 24 is 42? Yeah, I guess so. So there's 24 of these that are double counted. So these 24 are actually double counted. Doubled. Well, let me not write the word doubled. I'm going to say that my number 24 needs to also divide by a 2. Because of the fact that, if I said there's 18 of them which are legit over here, but the remaining 24, they're like counting the yellow and the blue, so I need to divide that by 2 to count how many actual edges there are. And when you divide by 2, then you get 12. And these are 12 doubled. That's how I want to think of it. Right? There are 12 of these edges double counted. That's how you got the 24. But what you actually do is the 18 plus the 12, and that finally matches the... Wait, is that right? I can't quite read. Yes, that matches 30. So now we know how to do this, and now let's try to do this for the big figure. The big figure is something where I need to go and say, I happen to have 20 smaller hexagons per side. Yikes. All right. If I want to do the same trick, I first need to know how many hexagons, and then I need to know how many edges there are on the boundary. How many hexagons are there? I guess these are called hexagonal numbers. So if there are 20 hexagons on a side, I have to do some more work, okay? So if I have 1 hexagon on a side, what I get is 1. There's 1 thing inside. If there are 2 hexagons a side, then you have 1 plus 6. That's what we saw here. What happens if you have 3 hexagons per side? This is how you solve all such problems. 1 plus 6 plus how much? Does anyone know what you add next? If it's 1 plus then 6, if I want to put 3 hexagons aside, I put another layer around this whole thing. What is that? It actually is 12, okay? And that makes sense because actually it should be a multiple of 6. It's symmetrical around 6 sides. And if you tried to draw it, let's try to draw little dots where they would go. These are the centers of the hexagons. 1 over here, 1 over there. Is that right? No. how would I do this? No, one over here. Yeah, one over here, one over here, right? That's how that would go. There's like those three across the top. And then I have this one over here. Oh, the easier way to think of this is that when there are three across a side, here's how you count them. There are three across a side, so here's two of them, and here's two of them. These are the centers of hexagons, okay? And then I have this one, and here's two of them. And if you see the way I'm drawing, I'm basically saying that, let's take this one. I'm basically saying that if I group them in batches of 2, I don't double count anything because there's like 3 on the side, and I don't want to use batches of 3 or I double count the endpoints. But that's how you see it's 1 plus 6 plus 12. And you guys want me to do what? These are huge numbers, guys. 20 smaller hexagons on a side? Okay. 20 hexagon aside. That's a weird way to write the word side. It has to be 1 plus 6 times, we're going to use parentheses now, 6 times 1 plus 2 plus, what's the last one that I should add? Do you see what I've done? I want to say these are multiples of 6. So it will be 6 times 1 plus 6 times 2 plus, what number goes here? 19. Thank you, everybody. 19. All right, what is this? I have to do some more multiplication? I guess so. So now I'll find out how many hexagons there are. If I want to know what this is, I do 1 plus 6 times. Now, the sum of this arithmetic progression is the first plus the last over 2. That's the average, by the way. Times how many there are. We're getting some crazy numbers now. Actually, I seem to remember this contest, you're allowed to use a calculator. Is that right? Are you allowed to use a calculator? I think that I heard that the rules are like you can use a 4-function calculator. So for that, we're going to pull out my 1-function calculator called my phone. Well, I mean, I was making a bad joke that it can do 1 function and the function is called anything. But anyway, let's try. So I want to actually do this, and I don't really want to go and worry about the exact answers. You might say, hey, how come I'm using my phone? Well, the reason is because I'm just going to go and use my very simple phone calculator, which is called the 4-function calculator in the phone. All right? So what do we have here? It will be 1 plus, if I calculate this out, whenever I type in, if I see a 20 divided by 2, I'm like, that's 10. So it's 1 plus 6 times 19 times 10. Whenever I type something into my calculator, I look at it carefully to make sure I type the same thing. What is the phone brand? Happens to be a Samsung. And this is 1141. Do people agree with me that this is 1141? That's the number of hexagons that we have. All right, so that's one of the things. The next thing we need to do is we need to know something about what's the perimeter, right? Because that's how many hexagons there are. This is how many hexagons. And so the number of edges would be that thing times 6. Let's multiply it by 6. But I have to break those edges into the perimeter and the things that are double counted. So including double counting, we have 1141 times 6 equals how much? 6846 edges. All right. So now I need to go and figure out what happens if I have, I need to figure out what happens with these single counted edges. So what's the perimeter like? How does the perimeter change? I need to look for some kind of a pattern for how I could find the perimeter of this guy when I only had, 2 on a side. I want to use something that's around the word 2. And if I want to focus on the 2 on a side, what if I did this? I'm just kind of looking at this, and I'm like, if I said that that was one of my sides, what would happen? Because that looks like 2, right? I did 2 of these hexagons. But you see, you do some double counting. Over here, it looks like this. And then over on the next one over, it looks like this. So it looks like what's going on is that if I want to find the perimeter, it was 2 on a side, and I could do 2 times 2 to get the 4. These are all 4s, but I did the double counting just 6 times. I'm trying to explain how I might explain this for if there are 20 on a side. If there are 20 on a side, you'd still get these nice long things, but you'd only overlap right there, like on this particular face, and on this face, and so on. You overlap 6 times. So what I'm saying is that the perimeter, let's get the next screen. if it's 20 hexagons on a side, the perimeter, I just mean the number of edges on the outside, okay? Let's not call it perimeter. The number of edges on the outside is equal to, it would be the same thing like 6 sides times 20 times 2, and then minus a 6. Are people okay with this calculation? Oh, what problems are being gone over again? Andrew Lee. Yes, this is from the Lexington Math Tournament. This is question number 7. And what we're doing is we're doing some really, really, really hard problems that you're supposed to have 6 days to do. And we're just kind of looking at them and trying to solve them, using the fact that there's like a few hundred people watching this live stream who already thought about them, who are giving us lots of hints. So, oh, somebody says they don't get it. I'm trying to find out how many, if there are 20 hexagons on a side, how many edges are on the outside? The pattern I noticed was that when I have 2 hexagons on a side, then if I want to find the number of edges on the outside, on the perimeter, then it's like the 2 times 2, because each of those hexagons gave me 2. So I should take, if it's 20 on the side, it's going to be 20 times 2. But this 6 here is because there are 6 sides of this hexagonal thing. And this minus 6 here, this minus 6 is because I do some double counting, like in this picture. In this picture, you can see that on this piece there will be a double count, on this piece there will be a double count, and when you go and expand the whole thing out, all that happens is that this yellow thing goes further out, the blue thing goes further out, the pink thing goes further out, but the overlap is just that one. Okay? So let's see what happens. If I do this, 6 times 20 times 2, oh, I'm too lazy to pull out my calculator. It's faster to look at this. To be honest, I'm a lazy guy. I don't like using my calculator. So the calculator is sometimes slower. 2 times 2 is 4, 4, 6 is 24. That's 240 minus 6, which is 234. I always go and double check. Does that make sense to me? That's a pretty number, by the way. Yeah, it looks right. 234. So I have 234, which are, oh yes, you're calling this strategic laziness. Really, let me tell you more about calculators. It's not just about lazy. It is so easy to type something into calculator and type it wrong. And when you type it wrong, you get an answer that looks legit, except it's just wrong. But here I like to just look. All right? So we've got now 234 of these that are counted once. And so now I just do the whole calculation I had. The calculator will come out now because my numbers get too big. So of these 6846 edges, there are 234 which are counted once. Great, that will be a number I use. And of the rest, there are 6846 minus 234, 6846 minus 234 divided by 2, which are double counted. Does that make sense to people? It's like these are the ones which I divide by 2 because it's like they're counted twice because they're inside. So I just need to go and figure out what this number is and add it to 234. Now the calculator comes out. Here we go, calculator. 6846 minus 234 equals. Always remember to press that equal sign if you're using one of these 4-function calculators, or else if you do the divide 2, you divided the 234 by 2. Now I divide by 2, I get 3306. That's not my final answer. That's my number doubled. That's my number of doubled edges. Finally, I take 3306 and I add it to 234. Okay, 3306 plus 234 equals, I seem to get 3540. I don't know if this is right or not. Let's go and ask. It's right! So this is good. So the answer to this actually is 3540. If you figured out this question, congratulations. This question has a lot of stuff embedded inside it. We have these arithmetic progressions, the sum of these 1 plus 2 plus whatevers, and we also have the idea of double counting. But in general, whenever you see something like this, the easiest way to do it is to say most of the edges are double counted, so I'll generally take an answer divided by 2. Just go and figure out what happens with the single counted stuff. What can we do next? Ooh, what's this? In the figure below, oops, did I click something? Hopefully it's okay. In the figure below, the large triangle and all 4 shaded triangles are equilateral. Let me make this bigger so I can see better. If the areas of the triangles A, B, and C are 1, 2, and 3 respectively, compute the smallest possible integer ratio between the area of the entire triangle to the area of triangle D. This is question number 12. What can we do here? When I look at something like this, I'm like, well, everything's equilateral. And I know something about the areas. And a little bit of it is also making me wonder, why are we even talking about the ratio between the area of the entire why is it the smallest possible integer ratio? Okay. I think I see why that is. All right, let's go and try to figure this out. So the first thing is that if I've got areas which are 1, 2, and 3, I guess I could figure out what each of those side lengths are. That's possible. And if you figure out what each of those side lengths are, I see. If you figure out what each of those side lengths are, you can figure out what is the height of the entire triangle. Here I need to tell you a cool fact. Okay, this is a really cool fact about equilateral triangles, which is going to be the heart of solving this problem. Look at my beautiful equilateral triangle. The bottom edge looks like it could use some help. Let's make it a bit more straight. All right, so we have this beautiful equilateral triangle. Did you know that if you take an equilateral triangle and you pick any point anywhere, like this one, and you go and calculate that length plus that length plus that length, that the sum of those three lengths is always the same? The height sum. Yes, this is in fact, sometimes if you look at a color picker, you might see, like if you're doing a drawing program, that there's a way to kind of choose a color, and maybe like this is one way that you're choosing a color. Actually, no, color pickers are usually circles. But this is like in some kind of a situation where you want three things to all add up to a constant. It turns out that no matter where you put this line in this point in the middle, the sum of the three heights is the same. And you know why? There's a really easy way to prove why. It's because you just have to draw these lines here. That's not a line. A little bit more straight. If I draw these three lines, the way you'd know that the three yellow lines all add up to the same thing is because I've just cut this equilateral triangle into three triangles based on the blue cuts. Areas, thank you very much. I am the one, 787, thank you very much. Okay, so these are all triangles, and the sum of the areas of the three triangles, the blue stuff that I cut, the sum of those three areas is the same as the area of the whole green thing. But what's the area of the blue triangles? It's actually half base times the little yellow height. So in fact, since all the bases are the same, if I go and move around where this point is in the middle, well, the sum of the heights has to be the same. That's a really quick proof of this. If you didn't get the proof, it's not a huge deal, but it's just a neat fact that the sum of these is all the same. Now that's what we're going to do here. So it's possible that the organizers of this problem had something more sophisticated in mind, but I'm just going to beat it. I'm just going to whack it with something. And so I'm going to say, look, if the area of triangle A is 1, let's go and figure out the height of triangle A. Okay, I got a triangle A, and the area is 1. Can I fit it up here? Maybe I can. Triangle A. If the area is 1, well, okay, so here's where it's helpful to maybe think about the relationship between the height and the area. Here's what I'll say. The height, if the height was x, because that's what I want to figure out anyway. If the height was x, does anyone know what this is? If x is the height of an equilateral triangle, how long is this length right there? It's not x. It's not x over 2. X over root 3. Yes, this is a 30, 60, 90 right triangle. You may notice that our math is getting more sophisticated now. In this daily live stream, we usually try not to go too far towards the high school level, but this is just a standard. It's a 30, 60, 90 right triangle where the ratio between that height and then this base over here is root 3 to 1. Okay, so that's x over root 3. From this, I can figure out what the area of the triangle is in terms of x. The area of the triangle is half base times height. And what I always like to do is if I already have half base, that's already half the base, I just go and multiply x times x over root 3. So I find that the area is equal to x squared over root 3. Whoa, that's interesting. So it will be a root of a root. We'll find out soon. So, okay, so x squared over root 3. So in that case, if I want to know what's the height, in terms of the area, now I can figure it out. Let's put it this way. The height, which is x, is equal to, looks like it's the root of a times the fourth root of 3. I didn't realize there would be a fourth root, but that's interesting. Okay, so if I ever am told an area, I can find out the height. The height will just be root of the thing, root of the area, times the fourth root of 3. So in that case, I now know a bunch of these heights. I know how long that distance is, I know how long that distance is, and I know how long that distance is. Let's see what happens. So we've got this height of A. I'm just drawing it here, so it looks sort of like the height of A. I hope that looks sort of like the height of A to you guys. But that height of A, that is equal to, the area of A was supposed to be 1, so it's just the fourth root of 3. I also have the height of B. The height of B is supposed to be like this. That looks like the height of B. The height of B will be square root of 2 times the fourth root of 3. And the height of C is this one. This is the square root of 3 times the fourth root of 3. Okay, now if I have all of these, why did I bother to do all of these? The reason is because I have one free variable I can play with, which is something to do about D. What would be the useful thing to do with D? Well, I'm going to do a ratio between the area of the entire triangle to the area of triangle D. So it could be useful to go and introduce a new length. And the new length, I'm not going to make the new length to be the height of D. I'm going to make the new length to be, I guess, from the edge of D to the middle of D. See what happens. Ah, how convenient. This drawing here, I actually can draw what I want. Let's say that I can still choose this. We'll call it X. Okay, so that part is X. Now, if that part is X, I could actually remember what the other things were. The other things were stuff like, this was something like, oops, that's not in the middle. Connect the middle to this. This thing was the fourth root of 3. This thing was square root of 2 times the fourth root of 3. And this thing was square root of 3 times the fourth root of 3. Now you see why I'm doing this. The reason I'm doing this is if that's X, I can figure out what's the height of the whole triangle. The way to find the height of the whole triangle is to use what we know, which is that no matter where I put this point, the sum of the 3 heights it makes are the same. I should probably have said, the point of that was, if I go back to here, what if I just put this one point at the corner? If you put it at the corner, then 2 of the yellow heights are 0, and the other yellow height is just the height of the triangle. So now what I can say is that if I had that to be X, if I had X for that length, this is also an X, and this is also an X. All those are X. So now I can say what is the height of the entire triangle. The height of the entire triangle is just the sum of all of these purple things plus 3 X's. Okay? And then that will tell me the height of the whole triangle. Height of the big. I got excited, so I wrote big in all caps. But the height of the big is equal to 3 X's plus, how much times fourth root of 3? Some stuff that won't fit. Let me write it underneath. Okay? So it's, oops, that's not what I wanted to do, but I can undo my way over there. The height of the big is 3 X's plus the fourth root of 3 times 1 plus the square root of 2 plus the square root of 3. Okay, now that's the height of the big. I also need to know what is the height of that little triangle in the middle. And I was curious, we were asked about the ratio of the area of the big over the area of the middle. Actually, what about the ratio? We were asked, what is the smallest possible integer ratio? So if I want the smallest possible integer ratio, I'll take the height of the big divided by the height of the small, square it, and then look at whether I can make that an integer. So that's the height of the big. What's the height of the small in terms of x? Does anyone know? I guess we need to do some scratch work. If I have the small is like this, small. That doesn't really look equilateral, but I think we get the idea. This is my x, and this is my x. But I'm curious about what happens for the height. And if I want the height, it's not exactly 3x, right? Because I've got x over here. I've got another x over there, but what I want to figure out is how much is this blue thing? If I could just add the blue thing, then that would be the height of the small. But what's the height of the blue thing in terms of the x? Well, it's another 30, 60, 90 right triangle. If that's x, then this is x over 2. It's nice. It's no more square roots. No more square roots will come from this part at least. This is x over 2. So in that case, I can tell you what's the height of the small. Height of small is just equal to 3/2 x. Great. Now what I do is I take the ratio of the top over the bottom and I square it. And I'm just curious how I can get an integer out of that. The reason I'm happy with this is because if I take this ratio, that part divides out really nicely. Right? If I take the ratio of this over this, the big over the small, the first part is just going to be 2. I'm just going to divide this whole thing by this 3/2 x. Okay? So let's see what happens. The ratio is equal to 2x plus, right, I'm just taking the yellow divided by the pink. So I get this divided by this is, no, it's not 2x, it's 2, not 2x, right? It's 2. So the 3x divided by 3/2 x is just 2 plus some nonsense. So that's going to be the 4th root of 3. Oh wait, I'm dividing by 3/2 x, so if I want to make some kind of a fraction, it'll be like 2/3. It'll look like this. 2/3, and then there will be a x, because I'm dividing by x, and it has the 4th root of 3 times 1 plus the square root of 2 plus the square root of 3. That's the ratio. Please correct me if you see a mistake, because as I've said, I haven't done these questions before, so that's probably what we should, it's very likely that I make a mistake along the way, but it seems like that's what I'd do. I take this divided by this, and I want to square that. And the question asks, how can I square that and get an integer? Right? I'm supposed to square that and get the smallest possible integer ratio. Well, in that case, it looks like I have a lot of choice in x, right? So I have 2 plus this, and I get to square it. So the area ratio, which is what I care about, the answer, area ratio, is going to be 2 plus this weird number, 2 times the 4th root of 3 times 1 plus the square root of 2 plus the square root of 3 divided by 3x. All squared. What's the smallest possible integer that this could be? At first you look at it and you say, what do you mean integer? If you made x to be like 5, it's going to be terrible. And if you made x to be like square root 3, it's also terrible. But the situation is, it's 2 plus something. No matter what I have x to be, this is going to be a positive number, right? It will be 2 plus something bigger than 0 and then square it. So no matter what, I can't make it 4, 3, 2, or 1 because, 2 plus 0 squared is 4. And so what's the smallest integer number that could be the square of this for like some very clever choice of x? Ivy thinks 5. You see, because if I made my x Google, like some huge number, if I made my x enormously huge, then this thing I'm adding is practically nothing, and I'm really close to 4. But if I go and let my x be smaller, at some point, if I'm super excited and I make my x to be like 0.00001, well, then this thing becomes huge. Like, if you divide by 0.0001, it's huge, right? And you take 2 plus huge, it's like huger, and you square it, and it's like super huge. Okay, so that means that the answer should be I should get some integer which is bigger than 4, and it could get like, as big as I want. So I'll say that the first number that I seem to find here looks like 5. Let's go and ask our assistant. Are we good? We are good! So the answer is 5. Yeah, so the answer happens to be 5. If you said 3, it's because you forgot to square it, right? We're talking about the smallest squared because, I'm sorry, that we want the smallest thing after you square because that's the ratio of the areas. All right, let's see what's next. What kind of question do we have? Ooh, lots of words. A country has 7 distinct cities. Who names their cities C1, C2 up to C7? I'll tell you who. Mathematicians. That's the best way to name cities. Don't call a city like, blah, 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 blah. Just go and use numbers. Between each pair of cities, they're going to choose a direction, and there's going to be a one-way road in that direction which connects the two cities. And after the construction is done, they found out that any city is reachable from any other city. That sounds like a good thing. Yeah, because otherwise you got a pretty lousy country. Okay, right. So it's found that any city is reachable from any other city. That is for any distinct, it just means that if I have any two cities, I can somehow drive from one to the other on the one-way roads. And find the number of ways that I could do this. So this is a graph theory problem. Actually, this kind of a problem, if you're trying to count the number of ways that you can make this way of putting the labels down, oh wow, this is question 28. That means this is pretty hard. Okay? If you want to know the number of ways to do this, you actually can have huge numbers. And the reason is because every one of those roads can be either one way or the other. So for every road potential, like for every pair of cities, you've got two choices. And it'll either be there or not. It'll be either one way or the other. Does anyone know how many pairs of roads there are between 7 cities? This is a quick check. This is a hard problem now, okay? We're probably going to spend a while doing it. But it's like, if I have 7 cities, then how many different pairs are there? It's actually 28. Let's just talk about that real quick, right? If I have 7 cities, that gives me, it's called 7 choose 2, which is 7 choose 2 pairs of cities. Each of those is going to need to have one way or the other. And 7 choose 2 happens to be, there are 7 ways to pick the first city, 6 ways to pick the second city you connect to, but you divide by 2 because you could have gone, when you count a pair, it could be that I picked this one first and then this one. Or it could be that I picked this one first and then this one. So you divide by 2. And that's 21. Okay? So that means that the answer is going to be less than or equal to the number of ways that I can pick the directions of 21 roads. 21 roads, if I want to pick the directions, each road is either one way or the other. So it's got 2 choices, and so I have 2 times 2 times 2 times 2 times 2, like 21 of these, 2 to the power 21 different possibilities that I could have. Right? There's 2 to the power 21 different ways to decide whether the road, to decide what the road network looks like. This is not the answer to the question, but what this tells me is that there are 2 to the power 21 ways to choose directions. But that's not what the question asked. The question said that somehow we need to go and make sure that that somehow everyone can kind of get to everyone. 2 to the 21, by the way, is a number that's approximately 2 million. So what that means is don't try to draw all of them. Whenever I see a problem like this, I guess what I'm interested in is, can we try to figure out what this means from a graph structure point of view? And maybe I have an unfair advantage over people in the sense that graph theorists think about this stuff a lot. I'm actually a network theorist, a graph theorist. And so when you look at this, what does this really mean? Whenever I have any kind of a network which has a bunch of directions, there's a very important concept. So this is a concept in graph theory where it says suppose I have all of these different things with some way to connect to other people and so on. What you can do is when you have any kind of a network with a bunch of these one-way edges, that's what they're called, one-way edges, you can go and you can take your network and you can cluster it. I'm just trying to draw an example, okay? You can go and take a very complicated network and you can cluster it into a bunch of blobs. So this is actually something way beyond what middle schoolers usually think about. But now you can. It's actually not rocket science. It's okay. We can all understand this. So what I'm trying to say is that if I have, let me do an example. I think that's the easiest. Okay, ignore what I just did here. Big eraser. I'm going to try to draw a simple example and explain to you what I mean. Suppose I had a network that looked like this. Nice loop over there, like this, and yeah. I think this is good. Something like this. Okay, so I just drew a network. By the way, in the actual problem, this would not be allowed because the actual problem, every single pair had a connection between them. Looks like a fish. You're making me hungry. Okay, I had fish for lunch. All right. Anyway, let's keep going. So if I have all of this thing here, and I'm just drawing a network. This network is not like a real network in the problem. In the problem, you actually had to have every pair either one way or the other. But if I draw this, I can take this network and I can start to analyze, who can get to who. And if I look at this, you see, this is a lump. Those people can all get to each other. Do you buy that? All those people can get to each other. Over here, all these people can get to each other. And here's a lonely person. It can get to itself. I've just taken this graph. Sorry, I'm calling it a graph. That's what these are called. You can call it a network if you want, but I took this network or this graph and I've broken it into these pieces, which sort of keep track of where you can get around. Is that making sense? So I've gotten these are where you could get around. And also, those are the biggest places you could get around. I can't go and make this blob bigger, or else it would not be true. If I took this block and I tried to include that one, if I tried to include like this, it would just not really be true that inside this spot you can go from anywhere to anywhere. Okay? So what I've actually done here is I've taken this network and I've broken it into some pieces where each piece is it's like a country almost of where you can get around. All right? I want to explain how this thing can change. So this thing that I've just done, if I just change some directions, the thing can look kind of different. Imagine what happens if I just take this and I flip it. I did one change. I flipped that. Now what happens? What's the smallest thing that you can get around to? Well, actually, once I did that, I think anyone can get anywhere. Wump. Does that make sense? I do this and it's right there. I get everything. You can get to everywhere, just like that. Let's do another example. Suppose this thing was, well, I guess that's actually probably enough examples. I'm just trying to explain that if I go and take something like this and I break into these different lumps, that's a useful concept. And the problem here is asking, how many ways can you do it so it breaks only into one lump? This suggests that maybe you should think about what happens if there's a bunch of different lumps. So if I happen to have a real situation like the problem where every possible pair is connected. So suppose every possible pair has something connected one way or the other. In that kind of a situation, what does the lump structure look like? So in the actual problem, suppose I found my lumps. And my lumps were here are some lumps. Suppose I got some lumps. And that's what it actually looks like. Very lumpy. Well said. So I've got all these lumps. And in all of these lumps, inside, I can kind of get from anywhere to anywhere. Inside each lump, you can get anywhere to anywhere. Inside this lump, you can get anywhere to anywhere, anywhere to anywhere, anywhere to anywhere. But remember, we're saying that in the problem, you can go from anywhere to anywhere else. In this problem, no, that's not what I'm saying. What I'm saying is that we're interested in studying the situation where I'm going to go and have every pair connected by an edge. Actually, what I want to say is the way I'm trying to solve this problem is I'm going to try to take the answer by saying, I've got these 2 to the power 21 ways. I want to break them apart. I want to categorize the 2 to the 21 ways based on the lump structure. Okay? So I'm going to say there's 2 to the 21 different possibilities, and they'll have weird lump structures. And ultimately, I want to go and figure out how many of them have the lump structure called just one lump. That's the game, all right? But suppose I have a bunch of lumps. If I have a bunch of lumps, look what happens in between. Here's a question. Can I ever have something like this? Is this ever okay? Well, this is not... If I saw this, then I should be no, you did a bad job with the lumps. You should just go and re-lump these two into a massive lump. Because if you make a massive lump out of this, it's still true that anyone could get to anyone else. If you wanted to go from this side to that side, you kind of go to that spot and then go over there, right? And if you wanted to go from this side to that side, just go to that airport over here and fly over to the other side, and you get there. So what I'm saying is that between lumps, you actually have to have the same kind of directionality. Is that okay? So it has to look like that. And in fact, all of them look like that. That's kind of neat. What else might happen? Here's a question. Would you ever be allowed to see this? Would that be possible? Well, obviously, because I'm asking the question, the answer is no, it's not possible. The reason it's not possible is because then I could get from anywhere here all the way back. In fact, I should go and lump the 3 lumps on top into one mega lump. Because if I wanted to go from here to there, I would just go to the spot here, fly over to there, walk over to the spot on there, fly over to there, and then I got there. Does that make sense? So what I've just found out, yes, this is the International Lump Port. Well said. So what I've just found out is that this lump diagram has some like weird directionality. So it turns out that the lump diagram has to be consistent. It turns out that this lump diagram has to be able to be laid out in a line. So if you actually finally draw your lump diagram, it wouldn't look like this. Your final lump diagram would look something like this. And somehow all of the planes in this International Lump Airport diagram, everything only flies from that side to that side. Does this make sense? I'm basically showing you a very interesting fact. It's if I take any one of these situations where I have a big network of things connected to things, and then I have these lumps, and every lump is something that like everyone in there can get to everyone else in there and back, then the lump structure has to go and lie in a straight line. And then after that, all the things go forward. Of course, if I drew it in a different way, all you do is you just rearrange this and just like pull the lumps, you can just move them around, and then you're like, aha, there we are. It looks like that. Okay. So in that case, if that's what's going on, then I've now found out that, interesting, I'll be able to break apart my 2 to the power 21 based on the lump structure. And now this is suggesting that I could try to solve a smaller problem. It's like, well, I've got to do this with 7, right? I've got 7 cities. Fortunately, 7 is a small number. What if I have smaller things? Oh, yeah, somebody's saying the lump on the right can't get to the lump on the left. Thank you for saying that. What I wanted to write here is I wanted to say there are 2 to the power 21 different ways that you could put roads if I didn't have to care about everyone being able to get to everywhere. So I'll say, let's take this 2 to the 21 and categorize it based on how much people are able to get from anywhere to anywhere else. Right? So in this particular example, this would not be one of the solutions that we count. We would not count this one in the answer because it's bad, because you can't get from this lump to the left lump. Actually, you can't even get from the right lump to the third lump, right? Aha! And I see that some people are having a suggestion. The suggestion is to use mathematical lumpduction. Oh, sorry, I slipped. A mathematical induction, or rather just or a recursion. We can go and try to figure this out by solving smaller problems. Again, I haven't done this problem yet, so this might not work. Let's go and try to find out. This is just like me being like, I think this thing might work. And 7 is small enough that we should be able to beat this one into the ground. So let's try. All right? We're going to try to do this thing with smaller numbers first. The first question is, what if there were only 2 cities? What's the answer, guys? If there are 2 cities, how many ways can I choose to put the direction of the roads or the road so that everywhere can go to everywhere? Not 2 lumps, I mean 2 cities. If there are 2 cities, like 2 dots, good luck. The answer is 0. Right? There's just like 2 cities, nothing you can do. There's like 1 road that goes from that way to that way. Those are called highways to nowhere. Actually, that's not true. That's a highway to that city. All that means is that, over time, everyone in the entire country ends up living in that city because they only just drive along the road and you just have everyone living there and the rest of the place is a ghost town. Now, suppose you have 3 cities. We somehow already knew the answer that was given to us. So if you have 3 cities, somehow your 3 cities are like C1, C2, C3, and you can either go around in one way or in the other way. We saw that already. There's 2. Now is where it starts to get harder. 4 cities. Now, I already know that there will be 2 to the power 4 choose 2 different possibilities with, like, the lump structure. Oh, wait, there's something I need to say. If there's one city, there's an answer here. There's one way. If there's one city, the number of ways you can make it so that everyone can get to themselves is actually, there's one way to do that. That's actually legit. It's called, see, I've got the one city, and there's no roads, but everyone can get from there to there. And that's also related to 2 to the power 0 is equal to 1. There's 0 different roads that we need to decide whether it's this way or that way, and 2 to the power 0 is 1. So you don't get why 2 cities is 0. Thanks for asking. If I have 2 cities, look, here are my 2 cities, and if I want to know how many ways can I put a direction between them so that there's always a way to get from one city to the other and always a way to get from the other city to the first, it wouldn't work. Like, you just can't, because you can only go one to the other. All right? So now, if I'm over here with 4 cities, how would that work? Well, there would be normally, like, how many different possibilities do I have to play with? I have 2 to the power 4 choose 2. Because there's like 4 different cities, 4 choose 2 pairs of cities, right? And that's equal to 2 to the power 4 times 3 over 2, which is equal to 2 to the power 6. Okay, that happens to be 64, but that's not important. That's the number of different ways to put the edges down, the directions down, but I don't know that that's the answer to how many ways that have like only one lump. So this is the number of ways to choose directions not caring about lumps. Okay, so now if I don't care about lumps, that's this huge number. But now let's start to break this apart. What does the lump structure look like? So suppose I've made the lump structure. Let's make some cases. So here's case 1. One lump. That would be the answer. Like, however many ways to make the one lump, that's like the answer for the 4 cities. Okay? But what if there isn't one lump? I could say 2 lumps. But 2 lumps is hard to think about. So I'm actually going to think, you see, I could lay out my lump structure. So if I'm laying out my lump structure, the way I might do this is I might say, right. So let's not write the case 1 yet. Let's just say that here's my lump structure, right? So in my lump structure for the 4 cities, it's something like this. And remember, there's an ordering. The lumps come in order. So it could, for example, be 3 cities and 1 city, or it could be 2 cities, and here's what I'm going to say. Over on the right side, I'm going to draw a rectangle and say 2 cities don't care how many lumps. Or I could have 1 city, and here I have 3 cities don't care how many lumps. And there's one more at the very front, which is 4 cities. Okay, I'm going to take a step back and try to make sure people can understand what this diagram means. In the 4 cities, I have 64 ways. Of these 64 ways, I'm going to take each of those ways and draw lump structures out of them. And when you draw lump structures out of them, then you have like some cities here, and they have names, by the way. These 3 cities could have, these could be like the city number C3 and C2 and C4. They have some names, right? These are the names of the cities, 3, 2, 4. And I guess this one here has the name, which is 1, because the cities are called 1, 2, 3, and 4. So now what's going on here is if I did this, then I'm going to have, like for my 4 cities, it's either one huge lump, which is what I want to say, that's my answer, or it's something like this, or it's something like this. And here I have 2 cities. Maybe these 2 are like called city number 2 and city number 4, and these might be city number 1 and city number 3. Okay, or I go over here, and maybe what happens here, somebody said Lumpington math tournament. You guys are so funny. So this could be 1, and this could be like 2, 3, and 4. I think what I'm trying to draw is I'm trying to draw a bunch of different possibilities where it's like you know, it could look like the first one or the second one or the third one or the fourth one. In this lumping thing with the 3, I don't really know what order those 3 are in, but I'm saying that those are the 3 cities in them. But why I'm doing this is because I can say once I drew this, I actually have enforced the directions between. All of these edges go like this. So now let me start to break this apart. How many ways can I have a picture that looks like the second one? A picture that looks like the second one works like this. I need to choose 3 of the cities to put in this lump. How many ways can I choose 3 cities? 4 choose 3, because there are 4 cities to choose from to choose which 3 are here. And then, after I have that, after I know what are those 3 cities, I'm going to use my answer for how many ways to make a 1 lump thing out of 3 cities. So I'll do times 2. And then, I will times how many ways there are to do this piece. The number of ways to do this piece, there's only 1 city. But what I'm going to write here is 2 to the power 1 choose 2. 1 choose 2 is 0. So what I've just done is I've said there are 4 choose 3 ways to decide which are the 3 cities in the first lump of size 3. And then after I've done that, then there's 2 ways, but this 2 is this 2. It's that there's a lump, and I already solved the problem before, so I'll use that one. And then now I do 2 to the power 1 choose 2, because I actually don't care whether this is just 1 lump or it just has one vertex or 1 city. So that's how many are in this piece. Before I calculate that, let's see how many are in this piece. In this piece, there are 4 choose 2, because there are 4 choose 2 ways to decide which are the 2 cities in the lump, times, how many ways could I do this? Oh, 0. Then I don't care anymore. But if I continued, I'll do 2 to the power 2 choose 2. Because that's why I drew a rectangle here. I don't even care what's going on here. I don't care whether there's 1 lump or 2 lumps inside this leftover 2 cities. It just doesn't matter. Because I just will say, in this particular category happens to be that we put these 2 first. Okay? Let's see. So if I did this, what happens with the next one? With the next one, I happen to have 4 choose 1 to decide which is that lucky city that's in the first lump in the front of size 1, and then times how many ways could I make a 1 lump? The number of ways is with 1. I mean, how many ways can I rearrange the edges in the 1 lump? There's just 1, the directions in 1 lump. Times, I've got 3 cities left, 2 to the power 3 choose 2. Okay, 2 to the power 3 choose 2. So then I have to go and say, look, how many are here? That's what I care about. That will be 64 minus all this stuff. What's this stuff? So this one here happens to be 4 choose 3, which is 4, times 2, which is 8, times another times 1, because 2 choose 0 is 1 choose 2 is 0. 2 to the 0 is 1. 4 times 2 is 8. This guy happens to be 0. And the last guy happens to be 4 times, what? Somebody help me here. 4 times 2 cubed, is that right? Which is 4 times 8. Wow, that's huge. 4 times 8 is 32. Is that right? So 4 times 2 cubed. Yeah, okay, 32. So let's add this together. 32 plus 8 is 40. So if I have 40 so far and there was 64 altogether, now I know there's 24. Hey, I remember somebody posting in the chat that there were 24. And the way I got this 24 was I took the 64 minus all this stuff. Okay? By the way, you should remember that this is a contest that you have 6 days to solve. But now what do? Let's just do it. So oh, that's 4 factorial. That's cute. But unfortunately, the answer for 3 is not 3 factorial. But once you see this, we're like, let's just do this at scale. I just have to do this to get up to 7. Whenever I do this in a math contest, I'm like, well, the computations are just do a few more. I only have to do this for 7. And so let's just power through it and see if it works. All right? So, okay. So we now know that we have 24 for 4 cities. What's the answer for 5 cities? 5 cities. Let's do the cases, right? We've got the mega lump. Oh yeah, first of all, the total. The total is equal to 2 to the power 5 choose 2. Because there are 5 different things, I take a pair. That happens to be 2 to the power 10, which is 1024. Okay, so now 1024. Now, what happens next? So, yes, tediousness is lumpy. There might be a more clever way. I'm just sharing with you how somebody would think their way through this if you were trying to just solve a problem like this on the spot. So the next thing that you could do is you could say, all right, so I've got the thing I don't know, which is the 5, but let's do it in the other order this time. If I have a 1 and 4, or if I have a lump of size 2 and 3, or I have a lump of size 3 and 2, or if I have a lump of size 4 and 1, or if I have the big lump of size 5, which is what I care about. Let's go and power through this, the incredible lump, temp ID says. So how many are in each? We'll do the same thing. So in the first one, how many ways could I be lucky to choose? How many ways can I choose the lucky one person? 5, choose 1. Times the number of ways that I can do with just one, the one lump, one vertex lump. There was one way to do that. That was the answer from before. There was, if I have a lump of size 1, how many ways could I choose the edges, directions? Just one way. Times 2 to the power 4 choose 2, because I don't care at all what's going on inside here. Okay? So the next one happens to be 5 choose 2. Times, how many ways could I do the 2? Oh, if I've got 2 cities, no ways I can do anything. Times 2 to the power 3 choose 2. The third one, 5 choose 3. Times, how many ways can I do the 3? The ways that you can do the 3 is, what was it? Oh, it was 2. Times 2 to the power 2 choose 2. This one is 5 choose 4. Times, how many ways could I do the 4? We just calculated 24. Times 2 to the power 1 choose 2. And then the bottom one I don't know. So let's just go and do it. Yes, so today's special, I'm over time, but we're going to get the answer. That's what I just want to show this and can get the answer, right? Oh, wait, this is not 64, this is 24, because I'm saying I already am enforcing that the first 4 are one lump, right? So the point is that I'm saying that I've got one lump here with 4 things. And I want to use the answer 24, which we had just figured out, which was if you have 4 cities, then there's 24 ways to make like those 4 cities into one lump. What is 1 choose 2? That's 0. There's no ways to choose 2 things from 1. And that makes sense. And that's also like the number of ways I could decide what to do with this. If I drew a picture like this and I had all the edges going that way, and I just put a vertex there, that counts. Let's calculate. Answer time. 5 choose 1 is 5. And then the 1 I don't care about. 4 choose 2 is 6. 2 to the power 6 is 64. Anyone know what this is? I think it's 320. Whenever I can avoid a calculator, I'll avoid a calculator. So what happens next? The next one is 5 choose 2, which is 10, times 0. Why am I bothering? The answer is 0. Okay? The next one is 5 choose 3, which is also 10. Now I'm going faster because at this point we're just calculating. Times 2 to the 1 is 2. This is 40. Correct me if I'm wrong. This one happens to be 5 choose 4, which is 5, times 24, times 1. And that happens to be 120. Multiplying by 5 is fun. You divide by 2 and you add a 0. So now let's just go and add all of these things. So let's add all of these things. 320 plus 40 plus 120. What is this? Help me, guys. 360, 480. Okay? So I've got 480 so far. Got to subtract 480 from 1024. And this equals something. Who can help me out with this? I'm going to subtract 500. I got 544. Is that right? 544. Okay. So now we just have to do it for 6, and then we do it for 7, and then we'll be done soon. I know that you can use a calculator for this, but it's just like, I mean, like somehow, oh wait, you said aren't the first, 4th, and 5th cases the same? The 1st, 4th, and 5th cases, not quite the same. What's going on here is we're just going by the size of the first lump. So all our calculations are going to look like this. We are over time. I know we're over time, but we just want to know what the answer is, okay? So if this is 5, and 5 is 544, all right. Let's go on. What's 6? It will just be the same pattern, right? It's going to be 6 choose 1, 6 choose 2, and 6 choose 3, and so on. So I'm going to skip over. There was another problem, but now I need some blank space. We'll get that. We'll skip over a bunch of space to get some more space. Let's go. Great. 6. We're not going to do that last problem. So if I've got 6 cities, okay, the total is equal to 2 to the power 6 choose 2. 6 choose 2 is 15. This is already quite big. 32, 7, 68. 6 choose 2 is 15, right? Yes, it's 15. Okay. Oh, what was the last answer? We got to jump all the way back. The last answer was 544. Let's keep going. 544. Now we do it again. And what I'm trying to show you is like, this is not necessarily the most efficient way to do it, but if you've got 6 days, this is pretty good. You'll be done fast. 6 cities, we have some cases. One case is there's the 1 lump, and then there's 5 more things which I don't care, or the 2 lumps, and then there's, sorry, the lump of size 2, or there's a lump of size 3, and then there's this 3 thing, or there's a lump of size 4, and there's a 2 thing, or there's a lump of size 5, and there's a 1 thing, or there's a mega lump, 6. Okay, let's go. Same thing that we do it again. Same thing, we do it again, and so this happens to be 6 choose 1 times the number of ways to do it for 1, which is 1, times 2 to the power 5 choose 2. Are people with me on this? This is like exactly what we're doing. This is what we did last time. 6 choose 1 to figure out who goes there, and then there's one way to fix it to make it go in the right way, times 2 to the power do anything you want over there. This is equal to 6 times 2 to the power 10. 2 to the power 10 is 1024. I think here I'm going to start using a calculator because the numbers are getting big. And we're almost done because we'll do 7 and we'll be done. So 6 times 1024 is equal to 6144. Next, let's just remember I'm going to times 0 here. There's going to be a 0 here because there's a 2. So this one was 0 from before. Next, 6 choose 3 times the number of ways to do it with the 3, which is 2. That was our answer from before. Times 2 to the power 3 choose 2, which is equal to 6 choose 3 is 6 times 5 times 4 divided by 6, which is 20, times 2 times 2 cubed, which is 8, which is what, 320? Maybe. Please correct me if this is wrong. 320. Then we have 6 choose 4 times the number of ways to do with 4. That was 24. Times 2 to the power 2 choose 2. And that is equal to 6 choose 4 is also 15, the same as 6 choose 2. Is that right? Yes, 6 choose 2 is 15. 15 times 24 times 2 to the power 1, which is 2. Right? Okay, 2 choose 2 is 1. Yeah, this is 2. And so what do we have here? 15 times 24 times 2. 15 times 24 times 2. 720. That feels right. Then I have 6 choose 5 times... How many ways were there to do with 5? Does anyone remember? Is there an easy closed form? You know, there probably is, but we'll find out. Let's go back. It's 544 here. So this is 544 times the number of ways to do 2 to the 1 choose 2. That's just 1. So this is 6 choose 5 is 6 times 544 times 2 to the, so that's just 1, and that's 6 times 544. This is 3264. And finally, let's figure out the answer. Subtract all of this from 32768. So I'll get 6144 plus 320 plus 720 plus 3264. So 6144 plus 320 plus 720 plus 3264. All of that was 10448. And plus, so subtract from 32768, I'm getting an answer of 32768 minus this 10448 of 22320. Do people agree with that? Yes, we do. And so now, what do we do here? So all we have to do is we just have to go and do it one more time. So what's the answer? 7 cities. So if I have 7 cities, I will have to have the huge number, which is 2 to the power 21. 7 cities is going to be 2 to the power 7 choose 2. 7 times 6 over 2, that's 2 to the 21 total. And then we just go and break this apart. 1, 6. And we just keep going. So 1/6, that would be 7 choose 1 times the number of ways to do with 1, which is 1, times 2 to the power 6 choose 2, which is equal to 7 times 1 times 2 to the power 6 times 5 over 2, which is 15. Wow, these are getting big. All right, so we have this. And then the next thing here is if the next one was with the 2, right? Let's just do all the cases. This 2 and 5. I'll just write like this now. 3 and 4, 4 and 3. This is why ordered pairs were invented. 5 and 2, 6 and 1, and the mega lump, 7. So this one's 0. The next one is 7 choose 3 times the number of ways to do with 3, which is 2, times 2 to the power 4 choose 2, which is equal to 7 times 6 times 5 over 6 is 35, times 2 to the power 6. Okay, what's that? We'll figure it out soon. And then the next one is 7 choose 4 times the number of ways to do 4, which was 24, times 2 to the power 3 choose 2, which is equal to 7 times 6. So 7 choose 4 is the same as 7 choose 3, because you either pick the 4 or you don't pick the 3. It's the same thing. 35 times 24 times 2 to the power 3, which is 8. All right? Then we have 7 choose 5 times, how many ways were there to do 5? Does anyone remember? 544. 544 times 2 to the power 2 choose 2, which is equal to 7 times 6. 7 choose 5 is 7 choose 2. That's 7 times 6 over 2, which is 21. Okay, times 544 times 2 to the 1, which is just 2. We're almost done. 7 choose 6 times, how many ways to do 6? 22320 times 2 to the power 1 choose 2, which is equal to 7 times 22320 times the number of ways 2 to the power 0 is 1. Okay, let's figure it out. What's the answer? So I just need to go and subtract everything, right? Let's go and add everything. So I've got 7 times 2 to the 15. That 2 to the power 15 is 32768. 7 times 2 to the 15. I have to add to that 35 times 2 to the 6, which is 64. Okay? Plus, I have to add to that 35 times 24 times 8. Well, these are huge. I have to add to that 21 times 544 times 2. And I have to add to that 7 times 22320. And let's see what we get. So when we add all of these together, I'm just reading my thing to make sure that what I typed in is exactly what I want to type in. 35 times 2 times 64. Okay, 35, 24, 8, 21. Okay, whenever I use a calculator, it's so hard to make sure I got it right. All of this together seems to be 419664. And so the question now is, does that actually work? 419664. So I need to know what is 2 to the 21. 2 to the power 21. Okay, where are we here? 2 to the power 21. That's like 2 million. Okay, and subtract 419664. And we get a weird number. When I subtract everything, the answer that comes out is 1677488. And it's right! It's right! Okay, so the answer is right. So my assistant has said the answer is right. And that's the correct answer. Now, is this the most efficient way to do this problem? I'm not sure. I'm actually kind of curious. I'll think again later. But I wanted to tell you, actually, the fact that we figured this out and didn't make any mistakes, and it was able to be solved with only 18 minutes overtime, is like, oh, this method works. This is what math is for. With math, if you just go and think through it and you're like, yep, that one's counting that, I accounted for everything, it will work. Then you can get everything. Is that the most efficient? Not necessarily. But the way I think about this is like, well, you've got 6 days. The answer is you're doing it for 7 of them. And if you're doing it for 7 of them, then presumably you could actually just do this. And I went very, very slowly. I went very slowly because it was just like, well, we want to make sure everything is right. By the way, if I ever saw something like this, I'd probably want to write a computer program to go and calculate it out. What you've just seen is you've just counted the number of ways to make what's called a strongly connected directed tournament. A strongly connected tournament. That's the technical term. But okay, I'm sure that the organizers have some very interesting ways to do these problems. What I wanted to do is I just wanted to use this chance to kind of highlight their wonderful work. Afterwards, I'm sure they'll send you the solutions, and you'll be able to be like, oh my gosh, this Po-Shen Loh that you can ask math anything to, those high school students are just so much better because their solutions are just so much more efficient. That's why I didn't want to look at them, because I want to let them show to you how good they are. What you've just watched is how Po-Shen Loh attempts to do the Lexington Math Tournament questions immediately. Sometimes it works, sometimes it doesn't work. But I, like many other people, will make mistakes and will not always find the best way to do something. I do strongly recommend that you follow the people who make this Lexington Math Tournament. They are really clever, and they will make a lot of nice things for you guys to play with. With that, I think we'll call it a day. Thank you to everyone who came to join us for this joint session between Ask Math Anything and Lexington Math Tournament. If you're new to this, we actually do something like this every single day, 4 o'clock to 5 o'clock. We usually end on time. 4 o'clock to 5 o'clock Eastern Time, every single day, Monday through Friday. And the usual format is people ask like random questions, and I just make random answers that hopefully are correct. If you like that format, please join. Tomorrow we'll have another session. It's the one where I kind of come out at 8 o'clock p.m. Eastern Time, and I talk about something mathematical that I've been thinking about recently, which is also a problem for you to think about. Maybe I'll see you there. And if not, I'll see you next time. Have a great evening, everyone.